So today I'm going to talk about extratropical storms in the limit of purely moist dynamics and how they respond to climate warming. So this is work with several collaborators, including in particular Matthew Cole from MIT, and this work is supported by the NSF. The main motivation for this work comes from the fact that the amount of water vapor in the atmosphere is very sensitive to climate warming. This is illustrated with some simulations across a wide range of climates on the left. What's shown is the column water vapor for a set of different simulations. Each simulation is a circle, and the black filled circle is close to present day climate in terms of temperature. Now, each simulation has been run with an idealized general circulation model, a snapshot of which is shown on the right. This is an aquaplanet. Use a simplified gray radiation and a relatively simple convection scheme from Fearson. And we're going to use this idealized general circulation model several times during the talk, so it's good to introduce it here. And then I'll just also point out that the dashed black line on the left shows what happens at constant relative humidity, which is pretty similar to what we see for the full column water vapor. And so really what's happening here is very simple. The temperature is going up, saturation vapor pressure is going up, and water vapor is going up in the atmosphere in a quasi-exponential fashion. And so the big question we'd like to address is, how does the resulting increase in latent heating as the climate warms affect extratropical storms? Now, latent heating depends not only on the amount of water vapor, but also vertical gradients of water vapor, on how strong the circulation is. But all of these do not change the basic fact that the amount of latent heating goes up as the climate warms. So let's go back to basic theory. So the classical theory of growth of extratropical eddies, including highs and lows, is based on normal modes of baroclinic instability in a dry atmosphere. And that's what's shown on the left. We've got geopotential height, top vertical velocity in the middle, and then temperature at the bottom, where C is cold and W is warm. And this is coming from the classic Eadie model. And what you see is that the warm air is rising, the cold air is sinking. The warm air is also being advected poleward, and the cold air is being advected equatorward. And because of all of this, the wave is growing exponentially in time. At the same time as, or roughly the same time as Eadie was publishing his work, Charney also published a similar model, and these really were revolutionary models in our understanding of cyclogenesis. Interestingly, as you can see on the quote on the right, Eadie didn't cite any papers other than a reference to Charney at the time, which I thought was perhaps, when I first saw this, because it was such a path-breaking work, but actually he just says, I'd rather not cite a long list of references. And when I teach this theory in my class in atmospheric dynamics, I advise students who may not want to try this in modern times. Okay, so what we'd like to do is use this kind of basic theory, but in a way that can be applied across different climates. And of course, that means we need to take into account moisture and latent heating. And so this is how we're going to do it based on the mean states from the climates from the idealized GCM I showed you earlier over a wide range of climates. And so this is following past work on dry baroclinic instability based on the sphere, and also on work including moisture, for example, from Manuel, Fantini, and Thorpe. And so how do we calculate modes of baroclinic instability? Well, we basically follow this recipe here. We start with an arbitrary small amplitude initial condition, an integration forward in time in the GCM. We fix the zonal mean state to the time mean state from the full GCM simulation for a given climate. So that's where the warming of the climate and the amount of water vapor and so on will come in. The small amplitude noise will grow to an eddy, and we want to keep it small amplitude for simplicity to get rid, and we don't want to have to worry about advective nonlinearity, at least at first. And so ever so often we rescale the size of the eddies to small amplitude. But we do include moisture. Ascending air is assumed to be saturated, descending air is dry. And so the effect of that is we get latent heating in the ascending air, as you can see in the cartoon here. So the resulting simulation will be nonlinear. Even though we don't have advective nonlinearity, we have nonlinearity from moisture. If we keep running this forward and rescaling, we get the fastest growing normal mode, which emerges, and that's the normal mode we're interested in.
So what does this look like? Well, we'll start with a very cool climate. And I'm going to show the vertical velocity just to illustrate these because it's quite sensitive to moisture. So this is the most unstable that emerges in very cold climate. And you see you have on the left a periodic wave in mid-latitudes. Red is up and blue is down. You can see the red and blue are a little bit different in size, but basically it's pretty symmetric in this very cold climate because there isn't that much water vapor, which would break the symmetry. And the right is just a cross-section of the vertical velocity at a particular latitude, and you can see this kind of wave number 6 pattern. So now we'll go to present-day climate type temperatures. And now you do see some differences between up and down. The up areas are much narrower and they're stronger, so overall mass must be conserved, so much air is going up as down, but we have a narrowing of the upward moving air. And so this is, you know, in terms of the most unstable mode, this is equivalent to what we see in present-day climate, and you can go a lot further in various ways, including more nonlinearity and so forth. But this is similar to present-day climate. And now if we keep warming it up, at first we just see the narrower region getting narrower and so on to some extent. But there isn't much change for a while. And then eventually, if you get to a hot climate, and even before that, you see a dramatic change. The fastest growing mode switches to a vortex mode, and you hopefully can see it right in the middle of the panel here. The strong ascent surrounded by descent. It's a bit easier to see in the cross section. You see the spike. And when we first saw this, we weren't quite sure what it was, and maybe it's wave number 1 or something like that. But really, it's actually just an isolated vortex. And it turns out that something that's been seen in models before, it's seen in observations. It's called a diabatic Rossby vortex. So that becomes the fastest growing mode in a warm enough and moist enough climate. So this is a fundamentally different type of instability. It's not like just the dry instability with some slight modification from latent heating. Latent heating is key to this type of instability. Basically, the latent heating replaces meridional advection of potential vorticity. We'll talk about what that means later. And the transition happens in terms of this GCM at a global mean surface temperature of about 300 Kelvin. But if you look at summer temperatures, sorry, I should say in terms of global mean temperature, that's very far away from where we are now. But if you look at seasonal temperatures and look in the, say, the northern hemisphere, it's not so far away from where we are now. It's not easy to make a direct comparison with this more idealized GCM. So I should say we're seeing this becoming fast-growing mode. It doesn't mean it has to completely dominate the solution. That's not what we see when we run the idealized GCM in warm climates, but it does mean that we should expect it to be a more important feature of the extratropical weather systems. So I mentioned this is seen in observations. I want to show you what that looks like. So this is a climatology from Butcher and Burnley from a number of years ago, showing on the left the Atlantic Basin and on the right the Pacific Basin. And then the shading is showing the number of these diabatic Rossby vortices that they identified with a special tracking algorithm. And then the points are where the genesis is in different seasons, depending whether it's black or open circles. So I should mention, you'll see in the caption, there's an alternative terminology. These are sometimes called diabatic Rossby wave. And so I'll use those interchangeably. Diabatic Rossby waves make sense as a name in that these propagate quite fast, and latent heating is replacing dry advection as the mechanism of the propagation. So that's why it makes sense, Rossby wave versus Rossby vortex. We really see these isolated structures, so it makes sense to us to call it a vortex, but both could make sense. And a famous example highlighted in a paper by Heini Wernli is the winter storm Lothar that went across the Atlantic, interacted with the jet stream and had a lot of impacts in Europe. But there's also been high impact events involving diabatic Rossby vortices on the east coast of the US, for example. So this is a video that Matthew made showing some development of diabatic Rossby vortices, two of them that start off near Florida. One of them goes north along off the coast of the US, and the other one goes across the Atlantic. And they later maybe developed into more complex storms, but at some point, according to the, in the main progression of these storms, according to the climatology from Butcher and Wernli, it is in fact, these are diabatic Rossby vortices. So hopefully this video will work over Zoom. So you can start things starting in this region and moving across the Atlantic like so. So that's the first one. But you can also see a second one that went here. So I think in Matthew's video, it will now actually start reversing, so you can kind of follow back to see where it came from, these two storms. And then it'll go forward, and you may want to look at this other storm that goes up here. So they can go quite quickly, zonally propagate, and also go more poleward. They're relatively small. They involve a lot of moist dynamics, so they're going to be more difficult to predict from a numerical weather prediction point of view. Okay, so for the rest of the talk, I wanted to address two questions about the diabatic Rossby vortex. And you can think about it as an extratropical storm with purely moist dynamics in this kind of a certain limit. So what is the structure of this diabatic Rossby vortex mode we found in the hot climate? How is it maintained by latent heating? And then, our main point here is we have a new theory for the diabatic Rossby vortex that predicts its growth rate and length scale as a function of the climate state, by which I mean the temperature profile and the humidity. So I'll start with what is the structure of this type of storm. And I'll just give a brief refresher on potential vorticity because I'll be using that a lot. And I know Sam Steckman talked about it in an earlier talk in this series. He was introducing a moist potential vorticity, or PV. Here we'll rely on the dry PV, but look at its sources and sinks from moisture. So potential vorticity, or PV, basically is a combined measure of the spin of the parcel of air in stratification, and it's conserved for adiabatic frictionless flow. So it involves the absolute vorticity and the gradient of theta, which mostly matters in the vertical. So the vertical gradient of theta is the largest part of that. So that's the first part. And then the second question is, well, how does latent heating affect potential vorticity? And the formula for it is given here. You can see it's proportional to the absolute vorticity, but it also involves a vertical gradient of theta dot. This is approximate, but this is kind of the dominant term. So if we have some latent heating represented by this cloud here, we'll tend to generate negative PV higher up above the maximum of the heating, and positive PV down below. So this is a really key factor for considering how latent heating affects extratropical storms, or affects storms in general. So we can then go to our normal mode, that's a diabatic Rossby vortex in the hot climate. And what's shown here in shading is the potential vorticity versus longitude and pressure. And what you see, the basic features is there's a very large anticyclonic or negative PV in the upper, middle, and upper troposphere. And then there's cyclonic PV in the lower troposphere. And then there's stuff going on in the boundary layer, which may not be very realistic. So I won't talk about as much about that. So that's the PV we see in the growing mode. And then we can also look at what latent heating is doing to generate PV, and that's shown in the contours. I should say the values here are all very small because this is coming from the small amplitude mode. We'll see some finite amplitude storms later. What you can see is as I promised, neglecting the boundary layer for simplicity, you see low levels, you get positive PV generation, upper levels, negative PV generation. And in general, the blue is overlying the blue and the red is overlying the red. So this is going to cause the storm to grow. So that's how the storm is growing. But you can also notice, that's the same point I just made, but you can also notice there's a phase shift. So the contours, the PV generation are a little bit offset from the maximum, say, in the PV itself, and the same in the red case, the positive PV is a little bit to the west where the generation is. And this is the classic picture of counter-propagating Rossby waves now in a moist context. We have westerly wind here, which all else being equal would just shear apart the whole structure. But this is normal mode that's keeping its structure. And so what's happening is the generation is a little bit to the west, so that tends to combat the westerly wind to some extent. Similarly here, the generation is a bit to the east. And so the whole structure will propagate to the east, but it can keep its same structure due to these slight offsets. So this fits in very nicely into our understanding of how normal modes grow in baroclinic instability in general, just with this twist that it's all happening through the latent heating. And we don't have a wave-like structure, we just have this isolated structure. So I mentioned that you do also see these kind of storms when you don't just calculate a small amplitude mode, but actually run the GCM into a statistical equilibrium. So I just wanted to, the storms aren't everywhere, but they do occur. So on the left, we have the small amplitude mode I was just talking about. And on the right, we have the storm in the simulation. And you can see, so this is just one storm we picked out. Now these PV values are very low over here in PV units, but over here, they're quite strong. And so you can see some similarities. We have the red positive PV down here. We have the blue positive PV up here. But there are also some differences. And the biggest one is that the blue negative PV, the anticyclonic PV, is much smaller in extent than what you see in the small amplitude mode. So, the generation is much smaller in extent, plus the PV itself. So what's going on here? Well, here's something I probably should have mentioned earlier, but in writing down the potential vorticity generation rate, one term is the term I focused on earlier, this kind of dipole term that's proportional to theta dot dz. But it also makes sense to include the upward advection. So there's strong upward motion going on in this storm, generating the latent heating. It makes sense, I think, and this follows from a classic paper by Hoskins in 1985, that you include this upward advection that's directly related to the latent heating. When you do that, that's what causing, and that effect is much more important for the finite amplitude storm because the anomalies are very large. So you're creating this strong positive PV anomaly down here. And that PV anomaly gets advected up as the storm develops and tends to decrease or wipe out the negative PV here, although it can't get rid of all of it. And that'll be important when we look at observations shortly. And this is something that's been seen before, for example, in tropical cyclones, it matters, or in other extratropical storms, but it's clearly playing a large role here. Okay, and lastly, what about the storms we do see in the current climate, the observed diabatic Rossby vortices, I've got picked two examples. One on the left is a winter storm, and on the right is a summer storm. So if we look at the summer storm first, you can see it's pretty similar to what we saw in the hot climate. This, I should say, is from ERA 5 reanalysis, I believe. It's pretty similar, although things don't extend as high up in the atmosphere. And that's just because water vapor is not extending as high up in the atmosphere because our climate isn't as warm as the hot climates I was showing you earlier. But you see the blue anomaly. It's not quite as clear, I would say, as in the mode or the GCM simulation, but generally the structure is pretty similar. However, if you look at the winter storm, now you really just see what you might call a red blob at the bottom. It's very surface confined. There really isn't much evidence of a negative PV feature here. And so this is a little perplexing, as you know, if it's growing, we would expect there to be a negative PV. However, as I mentioned, upward advection matters. So that has to be taken into account of the anomalies of PV. Also, the PV generation rate itself is dependent on the absolute vorticity, which will be much larger in the red part of this diagram. So there's reasons to believe it, that this is accurate, although these are reasonably small features, strongly diabatic in a reanalysis. So this is not directly observations. But we do speculate in our paper on this in JAS that this may explain why some of these DRVs that you see in observations or reanalysis tend to propagate more than they're growing. They are maintaining their strength against friction, but they're growing, but not as much as you might expect, and they are propagating very strongly. And that's what you'd expect if you have this kind of structure here. Okay, so that's some phenomenology of this diabatic Rossby vortex and how it's maintaining itself. And so we want to talk now about a theory for this diabatic Rossby vortex that predicts its growth rate and length scale as a function of the climate state. So what we do here is we work with the quasi-geostrophic two-layer model, which is, again, another classic model for baroclinic instability. And it will produce unstable baroclinic waves that grow in the presence of shear. So basically, we have two layers of the atmosphere. So you can view this as literally two layers, say, of constant entropy, or perhaps just as a very coarse discretization in the vertical. There's an upper flat boundary and a lower flat boundary. And then there's interface between the two layers, which will denote its height, eta. Because there's an interface that corresponds to a temperature gradient in the y direction, just like we have on Earth. So if you could think of this as the lower potential temperature layer at the bottom, and the upper layer is the higher potential temperature layer, as you go north to the right in this diagram, you're going to colder air. But because the thickness of the layer is changing, that also means the potential vorticity is changing. And so we get a PV gradient up here and a PV gradient of opposite sign in the lower layer. And it is the advection against those gradients that really generates the instability in a dry atmosphere. And so again, with this kind of model, you can run it fully nonlinearly. I'll show that later, but you can also drop the nonlinear advective terms to study the small amplitude instability. And that's what we'll do for now. And what we want to do is add moisture to this. And there's a few different ways you could do that. And I think we're going to do the simplest. What we're doing is probably the simplest way you could do it, which is to introduce a parameter or a function or in the thermodynamic equation. So this is an equation for potential temperature theta. Usually on the right, you would have latent heat release. But what we've done is we've replaced that by introducing this factor or, which is a function of W. It reduces to a scalar or when we have upward motion. So or could be, say, 0.1. And then when we have downward motion, it's 1. So the thermodynamic equation is just the usual thermodynamic equation. And so you can think of this as reducing the static stability in ascent regions. And this was introduced in Manuel Fantini and Thorpe, which is a classic paper on moist baroclinic instability. The parameter or over here, the scalar, can be derived as a function of temperature and pressure. So we generally know what that is. What makes this challenging mathematically is we now effectively have a nonlinear Heaviside function, which is nonlinear, and that means that or evolves with the flow, right? You have to know where you have ascent and descent. What was shown in the paper by Manuel Fantini and Thorpe is that in this kind of two-layer model, they actually did a semi-geostrophic model, but it's pretty similar in this quasi-geostrophic case. You get a periodic wave that's unstable. It has a faster growth rate than the dry model and a smaller ascent region than the dry model. So these were, you're basically getting a similar kind of wave, but it's been modified by latent heating. So we'd like to use the two-layer model, including latent heating, but get the regime where we get these diabatic Rossby vortices. And that is a little bit tricky in a two-layer model because you only have the two layers. But what we saw earlier is that the diabatically generated potential vorticity anomalies, that is the ones from latent heating, they're occurring in the interior of the atmosphere. So really what we need is a model for the interior of the atmosphere and something that's less focused on the boundaries. And it's hard to separate those two aspects in a two-layer model. Oh, sorry, I had one more slide I wanted to show you. I just wanted to show you how this parameter OR varies over the seasonal cycle in the current climate. This is from reanalysis. And what you can see is that, or it has to be between 0 and 1. If we look at the northern hemisphere, it's maybe 0.45 in winter, and it gets down to about 0.1 in summer. Southern hemisphere is a smaller seasonal cycle, but again, or is lower in winter. So that means, it's lower in summer. So in general, summer is hotter, more water vapor, more latent heating. So we expect OR to be lower, and that makes sense. If you go to a very warm climate in mid latitudes, you actually approach the limit of a moist adiabatic stratification, which is the OR tends to 0 limit. So the OR tends to 0 limit is quite interesting, both for summer in the current climate and also for thinking about climate change to a warmer climate. Okay, so how do we make this a model for diabatic Rossby vortices? Well, what we do is we take the simple approach of tilting the boundaries. So now it's the same kind of model. It has a tilt in the interface, which corresponds to a tilt or a temperature gradient, sorry. But now we have the exact same tilt in the upper boundary and in the lower boundary. And having done this and worked on it for a while, we actually discovered in retrospect that Francis Bretherton had suggested this idea as a way to separate out the issue of what are the PV gradients and what is the temperature gradient. You want to be able to control them. And what we want to control them in the sense that we want to look at the simplest case where the PV gradient is actually 0. So you'll notice the thickness of the layers in the basic state is now constant. So there's no PV gradient in the upper or lower layer. And here's the shear, the westerly winds that correspond to the basic state. So when we do this, we find that the unstable modes are now diabatic Rossby vortices, and we can study them. I should say we've also done the case where you have a tilt in the boundaries, but not quite this much, and then you get interesting transitions between the diabatic Rossby vortices and the more conventional wave-like instability, but I don't have time to get into that. But you could read more about that in our JAS paper. So here is the vertical. Here's an example when we time match forward the tilted 2-layer model for OR equals 0.01. So that's very strong latent heating. We don't have advection of wave-wave interaction, so advection of the wave by itself or the vortex by itself in this. And you just see as it goes forward, you'll see we start from some noisy condition. We see the emergence of these vortices. There's 3 of them currently, and if you keep going, you actually end up with just 1 vortex. This is the vertical velocity, so positive means a very strong upward motion. So this is very like what we saw in the general circulation model instability problem, but it's much, much simpler. We're now down to this 2-layer model, which essentially becomes almost a 1D model in terms of equations. So what does its potential vorticity anomalies and structure look like? So here's on the left is the vertical velocity, and then we're just going to focus in on the region where the vortex occurs. That's shown on the right here. So from x equals 5 to 9, so just right in this region. You see you have a positive PV in the lower layer, negative P in the upper layer, PV in the upper layer, and you see the diabatic generation is phase shifted just as we had in the GCM. Because it's a 2-layer model, it's QG. The upper, there's a certain symmetry between the upper and lower layers. You can flip the sign and get it. But apart from that, this seems like a pretty good model for the diabatic Rossby vortex. So just the mechanism of growth is very similar to what we saw earlier. We've got latent heating where there's upward motion, negative PV generation above, positive PV below, which generates positive PV. There's an offset that allows it to stay in the same place despite the shear. So with this kind of wind profile, the westerly winds, we won't actually get eastward propagation, but you could easily add on a positive view at both levels, and then you would get, again, the kind of realistic situation where the storms move to the east. So can we make progress analytically? The answer is yes. So you can combine the equations of the 2-layer model to just get an equation for W. That's a good thing to do because W is where the nonlinearity is in the small amplitude limit because of latent heating. So you want to focus on that variable. So it involves 4 derivatives, for example. Sigma is the growth rate. We also have a term here that matters, which you can view as a radiative cooling. It's balancing in the average, the latent heating that emerges in this diabatic Rossby vortex model, but didn't appear actually in the Manuel-Fantini-Thorpe type model for a moist wave, which is interesting. But we do need it here. And the main challenge in solving this is that these ors here depend on W, right? So this is very nonlinear. So we solve it in the following way. Here's a sketch. Here's W as a function of X, which you can think of as longitude. We have an ascent region where or is less than 1. We have a boundary at X equals B between the ascent region and the descent region. And then in the descent region out here, we have or equals 1. And then, you know, you can think of this as being having symmetry about the X equals 0 line. So we only need to solve one side of this vortex. And so at the boundary, you have to be careful to enforce the right matching conditions between the ascent and descent regions. Basically, we require a continuity of certain derivatives. And the other tricky thing about this technically is that we want to solve in the limit of a large domain. So it's an isolated vortex, but we take the limit of the domain size going to infinity. And it turned out to be very important to do that in just the right way to take that limit so you get correct mass continuity, mass conservation. So we can then derive a dispersion relation relating the growth rate and the length scale to or. That's what's shown here. The Ks are kind of like wave numbers. We're not assuming any kind of sinusoidal or exponential structure, but yeah, that's you get these Ks, which you can think of as being like wave numbers that appear. So this can be solved easily numerically to find the growth rate and the length scale. This closed form can be solved to find the growth rate and the length scale, but the to get actual explicit analytical expressions, you can look at the kind of interesting limit of or tends to 0, right? So you can think of that as the warm climate limit or a very hot summer limit. And so that's when latent heating really matters a lot. So here are the results for that. So as or tends to 0, on the left, we have the growth rate of a dry wave, no moisture at all. In the middle, a moist periodic wave where we do have PV gradients in the model, so it's not really the interior of the atmosphere. And that's what Manuel-Fantini-Thorpe found. And then, and Pablo Zorrilla-Gotter also had a very nice paper on this. And then on the right, you have the diabatic Rossby vortex. The top row is the growth rate non-dimensionally, and the bottom is in using a deformation radius and the shear, a reasonable shear to give dimensional values. So for a dry wave, it's 0.5 per day. Moist wave, it's larger, 1.28 times per day. And then a DRV, diabatic Rossby vortex, is nearly 2 per day. So it's much faster. So basically, the way to think about it is going from the dry to a moist wave. In this very moist limit, you get 2.5 times the growth rate. And then if you go to a diabatic Rossby vortex, you get another 1.5. So the DRV relative to the dry wave is 3.75 times faster in its growth. So we think this overall picture is consistent with the emergence of the DRV as the fastest growing mode in the warm limit of the GCM, because that is the structure, baroclinic structure that grows the fastest in that limit. You can also look at the length scale, and what we find here, and here it's going to be the length scale of the ascent region. It's the simplest thing to compare across the different types of disturbances. And what you see is basically in the limit of or tends to 0, very strong latent heating, the moist wave and the DRV have the same length scale, but they're much smaller than the dry wave. And as or tends to 0, the length scale actually goes to 0 in this model. So we're just giving you ascent lengths in kilometers for or a particular very small value or 0.01. So we think other things may come in to limit the length scale, but we get length scales about 200 kilometers for the DRV in that limit. One interesting question is, do you always get diabatic Rossby vortex solutions? Well, according to this model, no. If you look at the growth rate now solved numerically from the dispersion relation as a function of or, you can see it increases as or becomes smaller, stronger latent heating. But there's also this singular point here at 0.4 where the solution breaks down. If you look at the length scale, it just goes towards infinity as you get to that point. And so basically, if you look at the equations, you can see what's happening at r equals 0.38. You can get solutions for or below that value, and for or values larger than that, at least in an infinite domain, they don't exist anymore. And so this is quite interesting. There is this kind of transition between wave-like and vortex-like solutions has been seen before. For example, there's a paper by Lepere and Held, who also saw it in a different type of two-layer model. And so it's not clear how this threshold extends to the real world, for example, but it's certainly interesting. It's there in the two-layer model that we've developed. I would like to just kind of step back from the analytical results and say, well, why intuitively would you expect to go from an isolated vortex, from a wave to an isolated vortex mode when you have strong latent heating? And so this is a thought experiment to think about that question. So let's say if we started at the top here with a wave train of positive and negative PV anomalies, like so. Say this is in the lower layer of our model. Well, those positive and negative PV anomalies will generate meridional flow, so north and south flow between them. That will lead to, you can think of it as leading to upward motion and descent. And where you have upward motion, you'll get latent heating. But we saw earlier that latent heating will generate positive PV anomalies in the lower layer, but not negative PV anomalies, at least in the simplest case. And so those positive PV anomalies will tend to get amplified, and the negative anomalies will be weakened by this process. They're not zero, but they'll be weakened. So if we idealize this as showing just all positive PV anomalies, that's what you might end up, at least in an unstable mode. At the bottom, we have the alternate case where we just have one positive PV anomaly. And the question is, which will grow faster? Well, the series of positive PV anomalies has the unfortunate characteristic that between them, the induced flow from each of them tends to cancel out in terms of the meridional flow. And if you think of meridional flow being related to upward motion just by an isentropic upglide type of hypothesis, then this kind of situation is going to not lead to a strong upward motion as when you have just one vortex on its own. And so this argument suggests that an isolated anomaly is going to be the fastest growing mode of the system when latent heating is dominant. And it basically comes down to the fact that latent heating is generating PV of one sign in the lower layer and PV of only one sign in the upper layer. Whereas meridional advection, say in a dry wave, could generate PV anomalies of both signs in a given layer. Okay, lastly, I want to show some examples of when you run this tilted or untilted, actually gives somewhat similar results in a tilted two-layer model with strong latent heating. So on the left, I'm showing the vorticity, relative vorticity in the lower layer, a snapshot from a simulation. So we're not talking about unstable modes anymore, just running it forward with drag and radiative cooling and so on. And what you see is you have waves and maybe vortices in this dry limit. But when we go to the strong latent heating regime, we actually get what we might call a DRV world, in the same sense that people have dubbed tropical cyclone simulations in an F-plane, a tropical cyclone world. This seems to be a DRV world. So we get these much smaller vortices. Let me try and show you a movie of how this works. So now this is all for R equals 0.01, so very strong latent heating. The vorticities in the lower layer on the left, vertical velocity on the right. So you see the formation of these spikes in vertical velocity. They almost have these trails behind them. You can see these stronger red anomalies here to the left, and generally small-scale vortices. We know these are diabatic Rossby vortices because we've made composites of them or looked at their structure in detail, and that's what they are. You'll notice that they're propagating northward. Let me just show you that again. Oh, go back. So especially in the vertical velocity field, it's easy to see they're going northward. And that's because that's a nonlinear advection effect. You have a positive PV in the lower layer, it's offset from a negative PV in the upper layer. and they both induce velocities on each other that tends to push them north. So that's what we would expect. And if we had a more realistic base state winds, they would also go to the east. So the implication of these kind of simulations is that the DRV solution actually does become dominant in fully nonlinear simulations if you go to effectively a sufficiently warm climate. So we don't know, we know that's not quite what happens in the GCM. There might be more DRVs, but they might be stronger, but they're not dominating the flow. And so we think this is probably a difference between QG equations and primitive equations, depends on the Rossby number. And so there's a very interesting question, which Matthew and I are looking into as to how, as you vary Rossby number, which type of solution is the one that emerges. Okay, so to conclude, we've talked about these diabatic Rossby vortices in the present and hot climates. The effect of increasing water vapor on extratropical dynamics is really interesting one that's interested me for a long time. One aspect is the most unstable mode switches to a vortex in sufficiently hot and moist climates. So I think that's really fascinating. These vortices, diabatic Rossby vortex, represent the limit of purely moist dynamics, and they can be high impact storms in current climate. I think it's also useful to just to study these type of storms as a, the kind of a limiting case, but I think we may, by studying them, learn better to deal with moist dynamics, and that will help us for other storms that are affected by moisture, but are not quite as extreme in terms of their dynamics as DRVs. Our tilted two-layer model gives us some analytical results for the growth rate and length scale of diabatic Rossby vortices. So these were not available before. And what the main thing we find is that these DRVs grow faster than both the dry and moist waves when they occur. But they only occur for strong enough latent heating in the two-layer model, which is interesting. And so this preference for vortices over waves with strong latent heating, we think results from single-signed PV generation from the latent heating in each layer, as we illustrated over here. I think there's a lot of open questions in future work. So these DRVs in our current climate only, preferentially occur in certain seasons. They have hemispheric differences, seasonal differences, and we've got this growth rate. So there's been a lot of work in the past about trying to explain the distribution of storms, where storms grow, how fast they grow, using simple theory like the ED growth rate. So can we use this kind of theory to predict seasonality, geographic variation, climate change variation of diabatic Rossby vortices? And one interesting question is there a link to polar lows? Some polar lows look like moist baroclinic instability, not all. And so that could be an interesting thing to look at also. I mean, I think a big question is, does the frequency or strength of diabatic Rossby vortices increase as the climate warms in simulations and observed trends? We're looking into that. On the simulation side, it also would be interesting to look at it in observations. So, for the simulations, looking at more realistic simulations in summer, for example. And then I think theoretically, we still need to build up our understanding from two-layer QG theory, which we've got a theory for, to primitive equations, maybe semi-geostrophy in between as well could be interesting, and to observations. So we have some understanding, but we need to expand over a hierarchy of models and observations. Okay, so thank you very much. I will finish there. Sorry, I can't quite hear you. I don't know if it's just me.